Munich, and he'll be telling us about unavoidable CMB spectral features and blackbody photosphere of our universe.
I'm very pleased to be here because, we are living now in extremely interesting time. Yes, in extremely interesting time because technology evolves very rapidly, and things which was impossible even to dream 10 years ago are now becoming possible. At least great experimentalists agree to discuss them. Therefore, I will remind some old solutions which possibly will be observed in next 10-20 years. Great CMB, but I am glad that several people, including Jim Peebles, gave very good introduction to my talk, and they were especially telling how important it is that CMB has excellent blackbody spectrum. Till now, we do not see any deviation from the blackbody formula. And this is absolutely great, but I myself am absolutely sure that there are deviations. Question, what is the minimal level which we should detect in absolutely any case? First, what was obvious from the beginning, that adiabatic expansion of our universe preserves the blackbody spectrum, established at early times. And from the beginning, it was obvious that with some precision, it is possible to create blackbody during electron-positron annihilation, where you have amount of positrons exceeds 9 orders of magnitude amount of protons around us. This was important. But I remember how in 65 and 66, I tried to estimate what is the Rosseland free optical depth of the universe for CMB. And this was shock for me, because if you take into account only free, it was completely small up to time of positron-electron annihilation. What was surprise for me that Thompson optical depth was rather high, many orders of magnitude higher than free optical depth. Therefore, it was obvious that life is not easy, because in all courses in the university we heard that Thomson scattering doesn't create photons and doesn't absorb them and doesn't change energy. Something is wrong. But we know now that Compton scattering can do this if we take into account the changes of the frequency due to Doppler effect and due to recoil. This is very important. What are effects which we are taking into account? And in reality, there was people found this and did this in connection with the works on the hydrogen bomb, because they were very interesting what will be the upper temperature reached during this explosion, and they didn't knew that temperature will stop due to high Z ions in the atmosphere, and they were studying Comptonization, taking into account the second order Doppler, the shift of the photons due to the interaction with hotter electrons, and obviously recoil. But then, if we are thinking about blackbody spectrum, that there is another two important processes, Bremsstrahlung, free emission, and double Compton emission. This is the same. This process is first radiative correction to the scattering of electron onto nucleus, and this is first radiative correction to the scattering of photon onto electron. It's absolutely the same formula, everything is obvious. And our universe, when I started to work, this process was negligible because Hubble was 100, everything was baryons, and it was not important. But when now we are living in the universe where double Compton is at very high redshift, absolutely dominating over Bremsstrahlung, and this is key physical process. It's difficult for me not to mention Companiere's equation, because I learned a lot from the paper of published by companies, but made in the Zildovich group when they were working on hydrogen bomb. And there are, in this Fokker-Planck equation, there are three very important terms. One term is Doppler diffusion, you see it. This is beautiful term, is recoil, it's very simple. And this term, very difficult to understand, it's induced recoil term. I can tell you that I asked many times Zildovich and other people how they found it, and answer was very simple. Without this term, it's impossible to conserve black body during the radiation. Therefore, they introduced it. Physically, it's very, very complicated to explain it. Let's go further. And there are several solutions. If this term is not very important, then solution of Compane's equation just is Bose-Einstein equation. And I will speak a lot about Bose-Einstein equation. And here, mu is chemical potential, which shows you that you have deficiency of photons. You have more energy, but you cannot create photons. Then you have this Bose-Einstein spectrum. And two simplest and obvious solutions of Compane's equation. First is this, which is Y distortions. And everybody, Simon just was telling us about clusters of galaxies. We observe that brightness of the cluster is decreasing in the Rayleigh genes and increasing in the wind spectrum. It is just Y distortion when Y is small, and clusters are the case. But when Y parameter is large, then we have mu-type distortion, which is in reality just Bose-Einstein. You see how Bose-Einstein is going, but at low frequencies here, double Compton and free emission is trying to get black body Rayleigh genes brightness, you see here, and therefore we have this solution. It's a picture from the paper published in 1970. Why I'm speaking about this again? Look how strong are deviations here, and now people again are dreaming to detect these mu distortions. I have no time, but I will show you only one thing. This is a redshift, 1,000, 10,000, 100,000, million. Here, when redshift is higher than 100,000, Compton process can establish Bose-Einstein equilibrium. This is very important for us. Up to 10,000, we have only Y. He is intermediate. Now, Rishi Hartree, Jens Hlube, and me, we developed theory, some of it is analytical. What are the intermediate distortions here? And it's very informative part of this theory. In 1970, with Yakov Zildovich, we published this very simple solution, analytical solution, how mu distortions will be destroyed by the influence of Comptonization and production of photons due to Bremsstrahlung. This analytical formula now with Rishi Hartree, we have corrections to this formula. Here it is valid up to 7, I think, %, and new formula is better than 1%. Danese and Desotti use the same formula, put to double Compton. This is how exponentially mu rapidly decreases, and you see the black body surface. Black body surface is at redshift 2 million, and this very important characteristics of our universe. Practically any energy release here at higher redshifts, we cannot observe it. And from here, after redshift 2 million, we can see easily practically any energy release. To demonstrate this to you, I will give very simple example, electron-positron annihilation. You can read in every good physical cosmology book, starting from Jim Peebles' books, how much entropy was generated when all positrons disappeared in the universe. This was entropy and energy was much higher than the entropy in the radiation. And due to this black body photosphere, predicted deviations of the spectrum are only 10 in power 178. I tried to say, Rishi, maybe it's a little bigger, but he's saying that it's exactly this value. I can tell you, for me, no difference. It's 10 in power minus 40 or 10 in power minus 178. But 10 in power minus 78, you see how strong is this process. You know, there is a decay. 12 years is lifetime of tritium, but energy mu is only 10 in power minus 15. Beryllium-7 converts into the lithium-7 due to capture of K electron when recombination occurs. We computed this with Rishi, and you see here that energy release, there are beautiful lines, but energy release is only 10 power minus 16. What is important? This is in the standard theory. You're predicting how much energy will come from the dark matter annihilation. This value is already, it seems that experimentalists are able now to dream to detect this value. Silk dumping, absolutely great. It should be detected. And then I will tell few words about Bose condensation. It's negative when you have more photons than in the black body, and you have completely different type of distortion, if I will have time. Just to remind timing, this is the last scattering surface. You see it. This is the time when matter and radiation have similar energy densities. And this is black body photosphere. What we are proposing now, we are asking experimentally, this is our boundary, what we see today with Planck and with other spacecraft. Let us shift our boundary to this place, to 2 times 10 to the power 6. Every process which gave energy release here will be observed, and we will know a lot additional about our universe. I was coming to John Mather every 5 years after Kobe fired us and was asking him, what is possible? And he was telling me everything is difficult, difficult, difficult. Finally, during conference in Venice, where some people from here were, he agreed to say loudly that if he will get money for spacecraft, he can get better limits than fire us 2 or 3 orders of magnitude. I can tell you that progress is enormous. From the time of Venice meeting, 100 years of cosmology, and today, his estimates now are 6 times better than during that meeting. It is progress of technology of detectors and cryogenics. There are many theoretical models predicting significant energy release in the early universe. But I will speak today only about unavoidable. This, that your experiment in any case will get some success. Maybe trivial, but some success. These proposals, great proposal is PIXI. This from former John Mather group, and already in previous proposals, they were telling that Y, present day limit is of the order of 10 power minus 5, that they will go ahead 3 orders of magnitude in sensitivity. It's absolutely great, and they can do better, we know now. Europe is discussing core mission. You all heard about this, but I will show you what really we can measure if we will get such spacecrafts. First, this is the flux per hertz from the sky. This non-dimensional frequency, like in the clusters. You see at 219, we have, for Y parameter, we have 0 effect. And this is the Y distortion, red, and this is mu distortion. And you see that they are different, and good spectrometer can distinguish between them. This is important, and now I am showing you if Y is intermediate. We are not at Y type and not at mu type. We just in intermediate region. And this is on this plot how the crossing, when your signal is crossing through 0, how it is moving when we increasing Y. How minimal frequency is going, how maximal frequency is going. We can detect in reality time when energy occurred. Just observing this spectrum. We can get a lot of information from this. For example, it's very easy to, not very easy, it's possible to distinguish, excuse me, theoretically everything is easy. When you go from, when you have exponential decay and when you have power law, for example, silk type damping energy release, it's possible to distinguish them. May I say a few words about other beautiful spectral distortions which present-day cosmology is predicting? First, this visibility function. WMAP observed it, Planck knows where it is with huge precision. And this will be the emission where we expect at higher redshift, more than 1,500. We expect a lot of hydrogen lines, redshifted. Helium recombination, helium plus recombination, alpha particles. And it is possible to detect traces of these processes. And look, this is a spectrum, Lyman alpha line, H alpha line, Paschen alpha line, bracket line. And everything is in submillimeter and radio band. Exactly in our band, 1,500 times redshifted, and we can measure and prove, yes, really there was recombination. Even more, we can detect features which are connected with two recombinations in helium ion and helium atom. And we can prove it was there. Even more, we can say this is helium which never was inside stars. This is also possible, and this is beautiful science, I think. I can tell you that during last days, I was especially impressed by new data from ALMA. We heard about carbon 2 line, how great is it, and about many other lines. You see these fine structure lines. If during their ionization, first stars already supplied interstellar space with ions, not with ions, with these elements, then we have these ions, we have transitions, we can discuss how it's occurring, but this is the optical depth in lines and observed frequency. We thought that maybe Planck will detect it. I will show you directly what are the limits on abundance of ions from Planck. If Planck will reach level cross-calibrate channel with precision 10 in power minus 2 micro-K square. In that case, we can detect O3 on the level 4 times 10 in power minus 5 of solar abundance of oxygen. It will be possible to see at any given redshift how much elements, chemical elements were created. Planck, it seems that Planck is unable today to do this. Maybe somebody with new data, maybe it will come. But it is for devices of pixie type or of core type, it is possible, and this is great goal. At any redshift, you can put abundance of any ion in the interstellar space. Okay, this is, I can just mention two words about possibility of Bose-Einstein condensation of CMB photons. This is baryon cool faster than radiation. Therefore, radiation transfers energy to baryons to maintain equilibrium, and quantization gives us distortions of the type of Bose-Einstein. If we compare this with the silk damping, it's occurring. There were versions 2 years ago with Rishi Hartree and Jens Hluber. We were building this. There was a region where Bose-Einstein condensation was stronger than energy release due to silk. With NS 0.96, no chance. You see that silk is stronger than cooling of the baryons in the universe. It is also one of the results of Planck, which we see here, and which gives us good prediction. Okay, I will tell you only, all my conclusion is following. It seems that there is now a future for CMB spectroscopy, and let us wait for new experiments. I hope to survive and to see something interesting. Thank you.
Thanks very much. Questions? Martin?
Rashid, before you get to the level of sensitivity you would need for these exciting detections, would you not have to worry about many other kinds of foregrounds?
Yes.
Which are below the present level,
yes,
but maybe above that level?
Yes, I hadn't time to speak about this. I can tell you that life with Y parameter is extremely difficult, because in the even reionization, just only reionization, provides us with Y parameter on average on the sky 10 to the minus 7. It's only, you know, it's much higher than the limits PXC promises to us. It would be possible to do a nearby universe about which Simon was speaking. Present day map, Y map of the Planck, it shows that we are playing on the level 10 to the power minus 6, which is already very close to the Virus limit. And, but with mu distortion, I can tell you nothing is able to provide similar spectrum. Second, nothing is able to produce similar foreground as hydrogen, just Bohr atom shifted 1,500 times. You have great coding. And you understand, it is, I think that many things will be observed if you have sensitivity.
Reino?
Rashid, as you know, I mean, there were a number of experiments in the past for looking for distortions in the spectrum.
Yes.
And all of them were had negative results or upper limits. And most of them were looking for distortions at very low frequencies, like 2 gigahertz, 3 gigahertz. Now, do you think, what I've seen from what you are saying, that you have shifted the frequency where to look at higher frequencies. This yes. makes things very different. The question is, do you need to go to space to make such a kind of experiments, or would you like to start from ground?
I think that every experiment from ground is great because it's training people. You understand me? This is unique possibility to go ahead with technology and so on. And there are things which is practically impossible to do from space, very high resolution and so on. We're all waiting for CCAT. ALMA can do a lot. But I can tell you that space has its own attraction. Because from ground to make picture of the whole sky, as Planck did, is impossible. You understand me? And if we wish to get really great results, we need spacecraft for these purposes. For real cosmology, we need spacecraft. But it is absolutely necessary to continue efforts from the ground.
Okay, one more. Jean-Luc.
Rashid, when you showed the sensitivity needed to detect some of these lines, you also quote 20 arc-minute resolution. What is the reason for that?
Situation is the following. I am speaking about effect, which is destroying, which is, how to say, I see the absorption, how the acoustic peaks are disappearing. You understand me? This is, and therefore, because very big part of the signal is going around first peak,
okay,
it's good. This is the reason where I am getting the main gain from angular resolution.
But so it's still a statistical measurement over
yes.
a large part of the
yes.
sky.
Oh, I can do second thing. I can take all strong maxima and minima of Planck and work with them. So question is, what is, we have some contradiction yeah. with Rishi. I think it's better to work with maxima and minima. He is telling me theoretically no difference.
So the number is not, it looks low compared to what we do pixel per pixel, but it's not that low.
Yes.
From what we can get with photon noise limited detectors and larger arrays.
I think it is absolutely great because I do not know another method to measure chemical abundance at redshift 5, 12, 20, and this is direct method.
Okay, well let's thank Rashid again.
Thank you.